Today we'll talk about what we call function composition. And what function composition is the combination of two functions. So let's also think of that as function combination. We're combining two functions. We're not add, subtract, multiplying, or dividing, even though the symbols may look like that. It means combination. And what you'll see is a little bubble. You can see it in our examples. That bubble does not mean multiplication. It means composition. So when we see something like f and the little bubble g of x, that immediately means composition. That bubble means composition. And what we'll do is we'll replace that bubble with parentheses first of all, because then it will help us understand the order of composition. In function composition, we work from the inside out, or from the right to the left. So in this case, we would take whatever number we're told to plug into the g function, get an answer, and then take that result and plug it into f. So we're combining two functions, or composing two functions. Let's do some practice. And first we'll practice with basic function evaluation because it's been a while. So I'm given that f of x is x squared and g of x is 4 plus x. And we're going to use these two real basic functions just to learn about function composition. So first I'll evaluate f of negative 2. So that's just a reminder that I take negative 2 and I replace the x's in my f function with it. Well, here I'm taking my x, negative 2, and squaring it. Negative 2 squared is 4. And you're done. I would do the same with g of negative 2. I go to my g function and I replace x with negative 2. So this would be 4 plus negative 2, which is 2. So that's a quick review of just general function evaluation. For the rest of these, this is function composition. I know it because I see that new symbol. It means composition. And again, I'll replace that symbol every time with parentheses so that I'm reminded that in this case, I'm going to take 3, plug it into my g function, get a result, and take that result and plug it into f. PEMDAS, order of operations, says work from innermost parentheses out. So we're following rules of PEMDAS. So here I'll take 3 and plug it into my g function. And you need to show your work. So I'm going to say g of 3 is 4 plus 3, or 7. But I'm not done. I need to take that 7 and plug it into my f function. So now I'm going to find f of 7. Well, my f rule is square whatever comes in. So I'm going to take 7 and square it and get 49. Let's do another. In number 4, I'm going to reverse the order and do g of f of 3. So I replace that bubble with parentheses. I plug 3 into f first. So f of 3, f says whatever comes in, square it. f of 3 is 3 squared. 3 squared is 9. I take that result and I plug it into my g function. So now I'll evaluate g of 9. Well, g says 4 plus whatever comes in. So g of 9 is 4 plus 9, or 13. So these first two examples of function composition show us that composition is not commutative. When I plugged 3 in to f composed with g of 3, I got 49. When I switched the order of the composition, I got a different answer. So function composition is not commutative. That's a little fact you need to know. Let's do a couple more examples. So for number 5, I'm going to plug negative 5 into f, and then that result into g. I'm composing g of f of negative 5. So f of x says square what comes in, so I'm going to take negative 5 and square it, and get positive 25. Take that 25, plug it into g. G says do 4 plus whatever comes in. 4 plus 25 is 29. So g composed with f of negative 5 is 29 for these two functions. The functions will change. I'm just using the same two for examples. So g of negative 5, we'll take negative 5 and plug it into g. We'll do 4 plus negative 5 and get negative 1. Take that result and plug it into f. f of negative 1 is negative 1 squared, or 1. So again, I plugged the same numbers into my composition but reversed the order of composition and got different answers. Function composition is not commutative. For my last two examples, I don't plug in a number. I leave my function as g of f of x. And this is what we call finding the rule. And this will also help us with inverse functions later on. So in this case, I essentially take the rule for g of x, which is 4 plus x, and I plug it in to my f function. Well, my f function says whatever comes in, I square it. So I'm going to take 4 plus x and square it. It's a nice reminder of our binomial operations. I multiply that by itself and double distribute. So I'll end up with 16 plus 8x plus x squared. If you'd like to put that in standard form, you can, but you don't have to. So when I substitute in a variable, I get another expression. So what I could do now is, instead of using composition, if I plugged in if I wanted to do over here f of g of -5, I could plug it into this, because this is the rule for what we'll get every time. Okay, let's do another. Here I'm going to do g of f of x. So I'm going to take the rule for f of x, which is x squared, and plug it into my g function. Well, the rule for g says do 4 plus whatever comes in. So here I'll get 4 plus x squared. And I'm done. Well, the big question is, who cares? Who cares? Why are we making you do this function composition? Well, yesterday we talked about function inverses, and we have a check for function inverses. And the check is g and f, two different functions, are inverses of each other if and only if g composed with f of x gives you an x. So if I plug any number in, I get that same number out. And f composed with g of x gives you x back. So I do composition in both orders and get out what I put in. In general, you get an x out when you plug in to find a rule. And this is a big deal, and this is a big idea in checking function inverses. And I do think on the Algebra 2 exam, they won't just ask you to find composition. They're not going to ask you to plug in numbers. They want you to know these rules for checking inverses and be able to use them. So I'm going to show you that by checking yesterday's inverse work. So yesterday we had a function, f of x equals -2x plus 5, and we did some algebra on it, and we found that its inverse was -1/2 x plus 5/2. Yesterday we called that inverse f of x, and that's absolutely correct, and that's best. But just for the sake of composition, I renamed it g, but it's the same function. So what we're going to do to check our inverses is we're going to compose f of g of x, and we better get x back out, and we have to compose g of f of x and get x back out. If we do, both times, we have an inverse. If not, we made a mistake yesterday and should go back and fix it. Okay, so here I'm going to take my g of x rule, which is -1/2 x plus 5/2, and plug that in to my f function. So these start to look pretty scary, but you have to just be patient and do good algebra. So my f function says do -2 times whatever comes in. Well, what's coming in is this whole expression. So I'll take -2 times -1/2 x plus 5/2, and then we add 5 to it on the end. Okay, well, when I multiply -2 times -1/2, those two's cancel, and I'm left with +1x. -2 times +5/2, those two's cancel, and I'm left with -1 times 5, which is -5. So that's that part cleaned up, and then I add 5 to it. Well, we really write 1x as x, and -5 plus 5 cancels. So, although it looked scary in the beginning, it cleaned up fast, and I can say f of g of x equals x. So half of my inverse check is done, and it looks like we're in good shape, because I plugged in an x and I got out an x. But you have to do both orders. So here we'll do g composed with f of x. Well, the f of x rule is -2x plus 5. So I'm going to take that rule, and I'm going to plug it into my g functions variable. So my g function says -1/2 times whatever comes in. In this case, it's -2x plus 5. and then add 5/2 to it. So let's do some good algebra. Negative 1/2 times negative 2x. Negative times negative is positive. The 2's cancel, and I'm left with x. Negative 1/2 times positive 5 is negative 5/2. Then I add 5/2 at the end. Negative 5/2 plus 5/2 is 0, and I'm left with x. So g of f of x equals x, which means f and g are inverses. That is how we check for inverses. Have a great night. We'll do more in class tomorrow.